that was a very similar example to what we did before. We went from the function to the first and second derivatives. I'm going to extend this idea a little bit. Okay, when you turn over the page, I have not given you a function. I have given you a derivative, the first derivative, and we're going to draw some conclusions about what the function and what the second derivative are. Okay, so this is a little bit tricky, but we're going to think first about going from here to the second derivative, going to first to the second derivative. Okay, so firstly, I notice that this guy here has a turning point, right there. So what am I going to do with that? Where's that going to go? Think back to the ones we went before. It's going to go, number one, it's going to go down to here, because that means it's 0. But if the second derivative is 0, and everything's continuous, I have every reason to expect that in the actual function, I should have a point of inflection. So I'm going to draw my straight line up and down to indicate that. Okay, there you go. So I've got a rough idea of where things are going to go. That is going to tell me down here. It's got that. Now, so that I do not confuse it with the actual function, just coming back to my first page, I reserve these reds and greens. I reserve them for the actual function, okay? Because you can start to get confused when you talk about the gradient of the gradient, and which gradient is the gradient that you are graphing your gradient against. So don't confuse yourself. I'm going to keep all my colors up here, but in order to graph this second derivative positively, I do actually want to think about the gradient of the gradient function. Okay, so this guy here is increasing. I'm not using my color, I'm just using this so I don't confuse it with the top graph. It hits 0 and then it's decreasing. So what does that tell me about the regions down here for the second derivative? The regions down here, do they not correspond to the signs up here? Yeah, so I'm going to go positive here and negative here. You happy with that? Again, this is a straight line because I'm expecting this is more or less a quadratic. Okay, so I'm going to draw my straight line through. Okie dokie. Now that I've gone down, I'm going to use both of these to draw upwards. Okay, I've already identified where I'm expecting a point of inflection to be. Okay, when you look at the first derivative, the most important points on the first derivative are where they are 0. You see that? Okay. So I'm going to draw upwards from these two. This is where dy on dx is equal to 0. dy on dx is equal to 0 there, and it's also equal to 0 here. So this should tell me what about the actual function?
They're the maximum slash minimum points.
Yeah, they're stationary points, right? They may be max, they may be min, they may be horizontal points of inflection. I'll find out in a second, right? So I'm going to draw upwards. Okay, now this is great because what we're going to do is take all that formal thinking we've done before and use our logic to draw this graph. Okay? Now you can see I've got a stationary point here, right? Usually a traditional question would algebraically say, determine the nature of this stationary point. But you've already determined its nature. What have you used? You've done the second derivative, right? Look, you've got a stationary point. The second derivative is positive, which means it's concave up. Okay, so this corresponds to a minimum up here. Okay, so therefore, this is going to be a bit informal. I'm going to draw a low stationary point here. It's low because it's going to be a minimum, right? And just to indicate, I'm going to have sort of upturned edges to that stationary point. You see that? I don't know enough yet to join the dots properly, so I don't want to draw too much of it and mess myself up. And because I'm drawing in pen, which is a bit naughty. So I've got my minimum there. I come over here, there's another stationary point, right? And I have already determined its nature. The second derivative is negative, meaning it's concave down, right? So therefore, this guy up here is a max, yes? So I'm going to draw that stationary point higher, because it's a relative maximum. And then I've got these downturned bits here. You okay with that? Okay, excellent. I'm almost ready to go. In between here, from this stationary point to this stationary point, I have to go up. What do I have that corresponds to that in my derivatives?
It increases and then...
Yeah, good. So I've got this first derivative here is positive. You see that? So of course this part has to be increasing. All right, let's try and draw it, and as carefully as we can. We know where to expect the point of inflection. Let's give it a shot. Okay, so it's rough. I can't fix it now because it's in pen, but you can get the idea and you can obviously fix it up. You can do it lightly in pencil and then fix it up properly once you've got the whole picture there. Okay, so there's approximately my point of inflection. And again, you can informally say, yeah, that looks pretty concave down to me. I can back that up. And that also looks pretty concave up, even if it's a bit wiggly. Okay. All right, now on the outsides, let's think about this. Over here on the right of our maximum, what does the first derivative tell me? It's the first derivative is negative, meaning that this is decreasing. Like that, like a good healthy negative cubic should, right? And then on the left here, it's also decreasing, right, left to right, so it's coming down like so until it gets to the stationary point, which is also a turning point. And there it is, I'm done. You can of course verify it by doing this pattern from before. Look, I've got decreasing, 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 which maps to this. I've got increasing, 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 all the way up to the stationary point, which corresponds to here, and then decreasing, and I can do the same thing with the concavity. Where's the concavity? Concave up. Yeah. And I hit my stationary point, right? And then it looks pretty concave down to me. Question.
How do you know if it's like shifted up or down?
Okay, that's a fantastic question. Okay, and I'm so glad you asked it because otherwise I'd have to rhetorically ask myself. Remember, and let's get my whiteboard markers out. Remember, I very, very informally talked about this, and now is the right time to talk about it. Okay, if you differentiate a function like this, you know exactly what its derivative will be. Okay, you know that when you differentiate, okay, you're going to get no ambiguity 2x. dy on dx is 2x. Okay, now this is kind of what we were doing before in terms of you start with a function, then you go to its derivative, then you go to its second derivative. And again, there's no doubt, you know exactly what it has to be. Okay? But I've now placed you in a different position. I've placed you in this position, and I've said, now can you go back up? Can you go back up? And the problem is, well, it's not a problem, it's just reality. I could go back up to this guy, but I could go up to a whole series of other different functions as well. I could go up to this guy, right? Or I could just as equally go up to this guy. Okay. Okay. I could go up to this guy. I could go up to anything I like, so long as, come on, mathematician's favorite number. So long as, like, what binds all of these together is the x squared. What separates them all out, well, what does separate them all out? How would you word it? Yeah, it's the constant term hanging on the end, right? The y-intercept, exactly right, which just corresponds to vertical shift, okay? So what we do is you say, look at these guys, right? And this is the language I'm going to just tell you about quickly. Don't worry, it's not going to be in this particular test, but it's the right time to learn it. These are derivatives going down. Differentiate, 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 you get derivatives. If you go in the opposite direction, like these things that I came from, we call these guys, and maybe it is worth writing deep down, we call these primitives. This is where I came from. Yes, I have briefly mentioned this because on the assessment notifications, people said, hey, what's that about? That's what these are about, okay? Now, being that you told me, they've all got the x squared in common, all they differ by is a constant, okay? All of these primitives, this family of primitives, are all in the same form. They've all got an x squared, and then there's the addition of a constant, okay? Now, the constant is, well, it's to indicate that c is a constant and not a variable, we say c, hey, it's a real number. It's not just like, ooh, what's this pronumeral? No, it's an actual number. It could be 1 or minus 300 or minus pi, but it's a number, okay? And once you differentiate, you'll be there. Yep.
Does it have to be x squared?
From this derivative, yes, okay. That's right. So if I gave you a different derivative, if the derivative I gave you, and I've got other ones coming, if the derivative I gave you was say, well, what might this derivative be? Wait, sorry, this derivative, right? It's clearly a minus x squared, right? I guess, I don't know, it could be something like minus x minus 1x minus 2. That looks like the roots could be that, right? So that gives me the roots and that turns it upside down. Okay. Now this guy is going to have completely different primitives to this guy, right? As you can see, that top guy certainly doesn't look like x squared plus c to me, okay? But the important thing is, the question was, how do I know up or down where it is? And the answer is, it can be up or down any way you like. They're all valid primitives, okay? So I could have drawn this higher. I guess what this is saying is I don't know anything about these intercepts. They mean nothing to me, okay?